Hi, my name is Michael DeLong. Today we'll discuss Bernoulli's principle. This is my favorite of all scientific principles. But why? I mean, what is it? How does it work? And is it even useful? Well, let's find out. Bernoulli's principle states that an increase in the speed of a fluid will occur simultaneously with a decrease in its pressure. Fluid in this case is just about any gas or liquid substance, such as air and water. So now you know that things like air and water will experience a decrease in pressure when they are sped up. But can knowing this information somehow be useful to us? As it turns out, you can use Bernoulli's principle to drain a container of fluid. By causing air to move past the top end of a tube that is partially submerged in a fluid, you can make that fluid move up the tube and out the top. Would there be any practical application for this? I mean, couldn't you just turn the container upside down and empty it that way? I'm going to demonstrate Bernoulli's principle using this glass of water that's filled about a quarter of the way up a straw and compressed air. So as you can see, the cup was 1/4 of the way full, but it is now only 1/8 of the way full. What happened was that the compressed air going over the top of the straw lowered the air pressure inside the straw relative to the air pressure on the outside of the straw and inside of the cup. This caused the water to be pushed down and up the straw, or you could even say sucked up the straw and then sprayed out the top as a fine mist. Okay, so spraying water out of the end of a straw in the middle of a parking lot isn't all that practical, but the principle itself is. Think about it. Can you think of an item that you use on a daily basis that pulls fluid in a container up a partially submerged tube and sprays it out the top? Figured it out yet? No? Well, here's another clue. The fine mist that came out of the straw is the desired effect of this application of Bernoulli's principle. If you thought perfume, cologne, or cleaning sprays like Windex, well, pat yourself on the back. You figured it out. They used this exact methodology to create an atomized spray to evenly distribute the fluid over a given area. My grandfather was a mathematician, physicist, and an aerospace engineer. He worked for NASA and Lockheed. He was my idol as a child. Dinner time at his house was always filled with great stories about the trials and tribulations of the glory days of NASA. At some point, I had decided that I would grow up, become an aerospace engineer, and work for NASA just like him. Well, one day, riding in the backseat of my grandfather's car, he told me to stick my hand out of the window and tilt it slightly up. I was hypnotized by how strongly it wanted to fly away. The more I changed the angle of my hand up, the more it wanted to fly up. I could play this game for hours, or at least until I got a windburn. It wasn't until I was in 6th grade that I learned why this happens. I was reading a book on aerodynamics I had checked out from the school library. Coincidentally, my brother had checked out this very same book when he was at the same school 13 years earlier. His name in his handwriting was on the checkout card they kept in the front of the book. Anyway, this is when I discovered Bernoulli's principle, in that air going over the top of my hand was moving faster and at a lower pressure than the air going underneath. By the way, I'm 31 years old now, but I changed my mind about being an engineer in high school when I realized I wasn't crazy about all the math involved. Instead, I went into a different segment of the aviation industry that didn't require nearly as much math. This pressure differential caused my hand to be sucked upward, just like it would be pulled toward the vacuum cleaner hose if I put my hand close enough to it. You might ask, but Michael, isn't the air that's hitting the bottom of my hand what is really causing it to move upward? Isn't it just being pushed upward? I asked my grandfather this very same question one day. His answer to me was that despite what you might feel on the bottom of your hand, it was mostly being sucked upward by the pressure differential. The air hitting the bottom of your hand, though, isn't completely innocent. It does apply a force to your hand. It creates an aerodynamic force called drag that actually pushes more backward than upward. Anyway, the question remains, is this a practical application of Bernoulli's principle? Well, no, not really. I mean, it kept me entertained in the car as a child, and it helped to teach me a thing or two about aerodynamics and physics, but other than that, no, it really isn't all that useful. But hey, even at 31 years old, it is still fun to roll my windows down on a summer day, turn the radio up, and play with the wind. I mean, can you blame me? I'll wager $10 that you will drive somewhere today and do this. Or maybe you already have. So maybe sticking our hands out the window and playing with the wind isn't very useful. But we can take what we learned from the hand out the window silliness and do something very useful. How about we make airplanes fly? Isn't that practical? Well, of course. Airplanes make it so much easier to go long distances very quickly. My hand wants to fly when I stick it out the window. So what? A plane that weighs thousands of pounds is a completely different animal. My hand flying out the window as I drive down the highway does not prove that airplanes can be made to fly. So let's take a look at the science behind what does make airplanes fly. I am using an airfoil simulator provided by the Glenn Research Center at NASA. Relying upon my background in aviation and published statistics that are easily found by a Google search, I have entered the appropriate data points into the simulator in order to closely approximate the wing of a Cessna 172. A Cessna 172 is a single-propeller, 4-seat aircraft that is used by many student pilots learning to fly for the first time. It has a maximum takeoff weight of around 2,500 pounds. Now, pilots rarely try to take off at the maximum weight, so for the purposes of this demonstration, our Cessna 172 weighs about 2,000 pounds. So in order to overcome gravity, it will need to generate around 2,000 pounds of lift. The speed at which Cessna pilots usually pull back on the yoke and leap into the air is approximately 78 miles per hour, and once airborne, they usually climb at about 700 feet per minute. In this simulation, I will demonstrate Bernoulli's principle by simulating a takeoff in our Cessna 172. You will see that the speed of the air flowing over the top of the wing will increase relative to the speed of the air flowing underneath the wing. As a result, the gauge in the middle of the screen that measures lift in pounds will increase to around 2,000 pounds by the time we reach 78 miles per hour. We start out at 0 miles per hour at an altitude of 600 feet. Why 600 feet? For added realism, I set the altitude to 600 feet because that is approximately the average elevation above sea level here in the Dallas-Fort Worth area. We are 0 feet above ground, but we are 600 feet above sea level. Let's begin. I will increase the speed 10 miles per hour at a time. 10 miles per hour. 20 miles per hour. 30 miles per hour. 40 miles per hour. At this point, we're already halfway to takeoff speed, but we're not yet halfway to the amount of lift we need. Will we get enough lift by the time we get to 78 miles per hour to lift off? Or am I wrong about the speed that the airplane takes off at? Let's see. 50 miles per hour. 60 miles per hour. 70 miles per hour. 78 miles per hour. At this point, the wing is generating enough lift to equal gravity's downward pull on its mass. If your body was this airplane, you would probably feel the sensation of weightlessness. In case you're wondering, the reason we didn't have half the lift we needed by the time we hit the halfway mark on the speed, but we did by the time we got to the takeoff speed, lies in this number here the lift to drag ratio. More pounds of lift are generated for each mile per hour increase than there are pounds of drag created by that additional unit of velocity. That's important because if it were the other way around, you might never get off the ground before you ran out of runway. Anyway, that's a whole different topic for another day. All the pilot needs to do now is pull back on the yoke to increase the angle of the wing to about 10 degrees. This will increase the lift even more and cause it to rise into the air, climbing at about 700 feet per minute. But before we get off the ground, let's freeze the wind here and take a look at Bernoulli's principle in action. You can see that the column of white, yellow, and blue lines has shifted such that they are no longer directly on top of each other. For example, the yellow lines on top of the wing are much further ahead of the yellow lines on the bottom of the wing. Now, let's go ahead and do what pilots call rotate the airplane. We'll pretend to pull back on the yoke by increasing what this simulator calls angle. By the way, pilots call the angle of the wing relative to the horizon the plane's angle of attack. Pay close attention to the pounds of lift and the wind over the top of the wing as we rotate to 10 degrees. Wow, did you see the pounds of lift? It shot right up there, didn't it? The plane is now climbing up, up, and away. Also, do you see how much more dramatic the wind profile is over the top of the wing? Let's pause the wind one more time and compare it side by side to the wind profile when we were still on the ground. Well, there you have it. Now you know why airplanes fly. So, is Bernoulli's principle useful? Absolutely. As we just demonstrated, it's why airplanes fly. Empowered flight has allowed us to travel around the world faster than ever. That's very useful. Oh, empowered flight requires power, right? Bernoulli's principle is also how propellers on boats and airplanes generate thrust. Propellers are miniature wings that provide horizontal lift instead of vertical lift. Of course, ceiling fans, box fans, and basically every other kind of fan out there are a kind of propeller whose ability to function is explained by Bernoulli's principle. And did you know that baseball pitchers take advantage of Bernoulli's principle when they throw pitches that seem to dance in different directions? A pressure differential is created on one half of the ball by the various spinning motions pitchers are able to induce on the ball as it leaves their hand. The result is that the ball curves to one direction or even multiple directions. Have you ever ignored the yellow or red paint on the ground next to a subway or commuter train track? If you have, you've put yourself in more danger than you probably realize. A fast-moving train disturbs a massive volume of air as it moves. This can significantly lower the air pressure within a few feet of the train. Your brain interprets this as if you're being blown into the train, but really, you're being sucked into it. You can find videos of this horrible thing happening online, but I suggest you don't go looking for them. Just take my word for it. Bernoulli's principle showed us how to create handheld pumps that we can use to spray cleaning agents, cologne, and perfume. Have you ever fought with your shower curtain? The moving water creates a disturbance of air, and thus an area of low pressure inside the shower. Your shower curtain doesn't hate you or love you, it's just attracted to low pressure areas. Why doesn't smoke from a fire in a fireplace come out into the house? Fire creates hot air, and we all know that hot air rises. However, it can't rise out the chimney and into the house because the cooler, more stationary air inside the house is pulled into the low pressure area created by the rising hot air. The fire literally sucks air from the house into the fire and spits it out the chimney. In the old days, cars and airplanes used things called carburetors to suck fuel into the engine in a manner very similar to the compressed air, water, and straw demonstration I did earlier. Just pretend the water is gasoline, and instead of flying off into a parking lot, imagine that the atomized fuel-air mixture is going into the engine. Ever used a garden hose attachment to spray water halfway across the yard that otherwise would have just ejected a few inches from the hose before falling straight to the ground? Or how about partially covering up the end of the hose with your finger? The restriction introduced by the attachment or your finger causes the same amount of water to have to fit through a smaller hole. In order for the same amount of fluid to flow through this smaller area, it has to speed up. I hope you've enjoyed this video on Bernoulli's principle. At the beginning, I said this was my favorite scientific principle, and I hope you can see now why that is. This principle affects us in our everyday lives in ways we often don't even realize. We take for granted the world we live in. If you ever find yourself wondering why something works, go ahead, take a moment and ask Google for the answer. You'll be surprised what you will learn.